Hi everyone, I'm Tariq from School of Information Technology, Deakin University, Australia. Our paper title is Residual Multiscale Full Convolutional Network for High Resolution Semantic Segmentation of Retinal Vasculature. As shown in the picture, on the left we have a retinal fundus image as an input. The middle image is the ground truth or human annotation image, and the image on the right is our output image. A retinal fundus image includes various structures, including optic cup, optic disc, different pathological conditions, a network of vessels. The task is to segment vessels as similar as possible to the human annotation or the ground truth image. Retinal vessel segmentation is of vital importance in detecting vision-threatening retinal diseases. As can be seen, our method robustly predicts the vessel's pixels with considerable agreements with the human annotation. Retinal vessel segmentation is quite a challenging task. Here we show the prediction of state-of-the-art method from Orlando in comparison to the gold standard with a difference map shown in the last image. The difference map essentially shows the correct and false prediction by the state-of-the-art method. One challenge is to differentiate between the edge information of vessels and the edges of optic disc. It can be observed that state-of-the-art method falsely capture the OD edges as vessels. Another important problem is the tiny vessels that can be, in some cases, several pixels of width. As can be seen, that state-of-the-art method fails to detect majority of the vessels shown by the blue in color in the difference map that are tiny vessels. Pathologies in a retinal image can also pose an important problem. It can be observed from difference map that the state-of-the-art method is very sensitive to edges and also falsely captures pathologies as a part of vascular structure. Our goal is to come up with an automatic vessel segmentation method that can address the problems related to vessel segmentation and should effectively detect vessels under different varied conditions of optic cup, optic disc, should be able to detect tiny vessels, and it should not falsely detect these pathologies as vessels. In retinal vessel segmentation applications, the vessel size may vary considerably across patients with a variety of medical conditions. Diabetic retinopathy can cause the swelling of retinal vessels and can also encourage the development of smaller, newer ones. Hypertensive retinopathy, on the other hand, can cause the shrinking of retinal vessels. Neural networks in the literature often employ a single-sized convolutional network, which often focuses in the larger vessels and therefore is not quite effective for the segmentation of smaller vascular structures. Several diagnoses in medical applications heavily rely upon the small size vessels. So in order to achieve or segment these small size vessels under varied conditions, we propose a multi-scale architecture that consists of 3x3, 5x5, and 7x7 convolutions for large and medium and small size vessels respectively. We adapt several steps to achieve this, and the first of these is to keep a minimum use of pooling layers, which are used to reduce the dimension of feature maps. This is since these pooling operations also cause the loss of spatial information. Secondly, we employed multiscale kernels so as to account for large variations in in retinal vessel sizes. Thirdly, we reduce the overall number of convolutions in the network. These can also be responsible for spatial information loss. And finally, we employ fine-grained information and residual skip paths to improve the segmentation results and make training more computationally efficient. And these residual paths includes the internal as well as external skip connections. If we further look at this one particular multiscale block, so it is basically comprising these three convolutional filters of three different kernels, 3x3, which actually C3A, 5x5, C5A, and 7x7, C7A. So after convolution, we obtain this S, which we can view as a combined feature map, which can later be fed to a ReLU and batch normalization. This is done after an additional convolution C3B, which is applied so as to obtain the feature map S dash, where S dash is multi-scale feature map. To further improve the feature map quality, S dash is combined with this F dash, which is basically a outer skip connection of 1x1 convolution kernel. And we finally combined this S dash and F dash, and we got this a feature map set, which is then fed to the next block, and so on. We did further in the same way we did these further multiple multi-scale convolutions. For training, we use Adam as proposed by Kima. The learning rate of we selected was 2e raised to power minus 4 and b1 was 0.5. For augmentation, we used the rotations from 1 till almost flipping and rotations, and with different 3-degree like differences in rotation we used from 0 to 360, and then intensity variation as well. All our experiments were performed using 8 NVIDIA GTX 1080 Ti GPUs with 11 GB of memory, and the network has been implemented on MATLAB. We used 3 publicly available datasets, Tariq, Syed, and the Chase. And following proposed by saying ETL evaluation criteria were used with TP, FN, TN, and FP to calculate sensitivity, specificity, and accuracy. Visual results for Thrive, we choose 2 images, image 1 and image 3. In image 3, we can see some pathologies. In image 1, there are some tiny vessels. So we can observe from image 3 that in the pathologies, still our method is able to differentiate between the pathologies and the vessels. For stair, we used 2 images, image 1 and image 2 as sample images. And the results, both images contain pathologies, and we can see that under these pathological conditions, still our method is able to detect vessels effectively, and it can differentiate between pathologies and the vessels. And the third, on Chase, again, our method is effectively able to detect vessels under different conditions. Numerical results of the drive data shows the superiority of these proposed methods on all the parameters, including sensitivity, specificity, accuracy, and AUC. We can see a huge difference in terms of accuracy between the state-of-the-art methods and the proposed methods. And in terms of sensitivity, it's quite competitive with GUETL, much slight better. And so if we look at the stair results again, the proposed method stair results, sensitivity is quite high. Comparable, the other comparable is from Epsilon BestNet, but other parameters also quite high. Then the accuracy is 97.9739, which is quite high as compared to all the state-of-the-art methods of 2018, 19, and 20. On the Chase dataset, again, we got quite impressive results in the state-of-the-art methods of 2019 and 2020. So in conclusion, this paper presented a residual multiscale network for retinal vessel segmentation that employs skip connections, multiscale filters, reduced number of pooling operations to segment large, medium, and thin vasculature under variation of contrast, optic disposition, and size. As a result, we got boosted detection accuracy and competitive performance, and fine segmentation performance even with the tiny vessels. Thanks for watching this video.